Hey folks, welcome back to my channel. In this video I'm going to show you guys how can you build your linear regression model using R. So this video is going to be a comprehensive video that's going to include all of your linear regression results. For example, what is your R square, what is your p-value, what is your residual error, f-static, all of that. Plus I'm also going to show you guys how can you predict your values from your model and then analyze if the prediction is good or not. Right, so let's go ahead and get it started right now. So first thing, like my previous other modeling videos, I'm going to use the Boston housing data set. So I'm just going to go ahead and build a input variable. So let's read the data inside. Let's take a look into the data. Alright, so this data here, it has 14 different variables and 506 observations. So it just talks about the housing market in the Boston area in the United States. In this video I'm going to get the MEDV is going to be my interested output variable, and then I'm going to use LStat to predict MEDV. So LStat is going to be my input variable or X, and MEDV is going to be Y. Right, so MEDV stands for median value of your houses, and LStat stands for lower status of the population. Right, so I'm going to use these two guys to find the MEDV. In fact, I can also use age on any of that if you want to do multiple regression, but we can use LStat and MEDV as our main variables, and we can always add and drop other variables as needed. So first things first, let's take a look into a summary as to how the data looks like. These two is going to be where my interest is, plus I can also choose age for my prediction. So LStat, the minimum is going to be 1.73, the maximum is 37.97, and then we have some median values around 11 like that. And then again MEDV, the minimum is 5, the maximum is 50, and then in the middle we have 21 like that. We'll also choose age. No, we'll do a multiple regression. So min is 2.90, max is 100, and then in between we have around 77 like that. Apart from that, I also wanted to show you guys the plot of this. So let's just say data in. I'm gonna use MEDV and then data in, and then I'm gonna use LStat, so X and Y variables to plot. So this shows us the full plot of it. So this is the full plot of what we have right now for between my LStat and MEDV. What I'm going to do is I'm going to go ahead and build the model right now. I'm going to show you guys where my linear regression line stands for. As you might know, the linear regression is basically your y is equal to mx plus c. Right, so y is your here MEDV, and then x is going to be your LStat, and then m is going to be your slope of how the line is going to be drawn, and then c is your constant. Right, so I'm going to show you guys how this specific line corresponds to this data, and then how that is going to get plotted over this x and y variables here. Right, alright, so first things first. For model building, first thing is your data partitioning. So let's do a data partition. So in my previous video on Logistic Regression, I have used Stratified Random sampling. You can take a look into that. I have used the caret library for using the create data partition function. In this one, I'm just going to use a simple random sampling since it's a numerical data. MEDV is a numerical, right? So I'm just going to use simple random sampling. So it's super easy actually to partition. I'll show you guys right now. So first thing is you need to create a partition service variable. Let's just call it P1. It's just gonna, these are not functional variables, it's just for us to do the help us to partition. I'm just gonna create P1, and then I'm gonna say run if. Run if is the function, and then I'm gonna say what is the total number of rows within this, and then create me some random numbers for those many number of rows. So instead of n row, right, you can also say 506. Right, you can just put 506 in place of this, It's all the same thing, but I can also do just for simplicity, instead of this I can put 506, right? And it's going to create some 506 random numbers, something like this, right? So if I run P1, you see it just some random 506 numbers. It just creates some random numbers just like that, right? But this is my P1. I'm gonna use another service variable called P2, in which I'm gonna order my P1. Why am I doing that? I'll show you in a few seconds. So if you take a look into my P2, it just stores the index, right? These are just the indexes of different values here. So 0.7454, right, has to be the 240th number. As per when it orders it, that is a 240th number. So 0.7454, this last number, right? And then this one, 0.5767, is basically a 352nd number, right? And likewise, your first one is going to be 299, right? So this one here, wait, where is that? Okay, so this one here is going to be your 299th record. So that is what I'm doing here. But I'm doing this because I'm going to use this. I'm going to use my shuffled values. I'm going to use these random indexes to shuffle up the data inside my data in, right? Just to create some randomness in selection, right? Let's create the training data set. Training data set is equal to, the data is going to come from the data in, right? There's no thing in that. And then the indexes are going to be chosen from P2, right? Within P2, I'm going to choose, you know what, we have 506 records. I'm going to choose, let's say, first 350 records, right? So let's say 1 all the way until 350. So it starts from 1 and it goes all the way until 350 within this. So it's basically going to take this number and all the way until 352 is that, which means 350 is these two, right? I think, or even including 70. So it's going to take the first 350 values from P2, right? And it's going to just assign it. It's going to take it from the data inside, only these numbers. So 299th record from data in will be taken, 271st will be taken, 28th record will be taken, 87th is taken, 414 is taken. So it's completely random selection from your data in, right? So that's all you're doing here. And then I'm gonna do it, get all the columns. So command nulls gives me all the columns. Alright, so my training data set is created. As you can see, it has 316 observations random, you see here. So exactly what you have here. So 299th record has been chosen, 271st record has been chosen, 20th has been chosen, and all the way, right? So random selection. So that's the advantage of using the runif command. So likewise, I'm also going to choose a training data set. Similarly, from the data in, I'm going to choose the indexes from my P2 variable. In this one, I'm going to choose the records from 351 all the way until 506, right? So that's all I'm going to have. So now let's take a look into my test data set. So I have 156 records, perfect. Again, random selection, just like the one before, right? Clean. Alright, so next one, what I'm going to do is basically, now that we have partitioned the data set, which is the primary step in model building, next one is let's go ahead and build the model, right? So I'm going to call this as, Boston housing regression, right? That's the name of my model. The function is LM. LM is a linear model. It's super simple to keep in mind. LM linear model, since you are building a linear regression. Alright, so I'm going to use MEDV. That is going to be my output variable, and use a tilde sign to differentiate between my output and input. LStat is my input variable, and then I can also, as we discussed, I'm also going to add age with it. So if you just use LStat, it's going to be single imputation. Since I'm adding age to it, now it becomes multiple imputation, right? And the data is going to come from this time, since model building, I'm going to use a training data set. First let's train the model, and then when we test the model, the data pattern will all be memorized by the engine, and then when we test it, it's gonna give us amazing prediction results, right? So that's the expectation. Alright, so now that the model has been built, now I want to show you guys, before I'm gonna jump into the summary and explain what is R square, what is RMSE and all of that, I wanted to show you guys how does it look when you plot your line in your plot here. So let's use an AB line, and then let's just plot this guy here. So you see it's looks like we have a negative slope. I'm gonna show you guys a little bit, add a little bit more clarity to that. It's not clean. Okay, so if you see here, so this is basically your linear regression line, right? So this intercept is looks like the y-intercept is around 32, 33 like that, and then it's negative slope, so the slope is going to be negative for LSTAT. So that's what we have here. Alright, so now let's take a look into the summary. Summary of my model, and then let's see. Okay. Alright, so first things first, what you have here is basically first thing is your function call, right? And then you have your residuals. Residuals are basically, what are these, right? So residuals are basically the difference between your predicted value, right, which is the fitted value, and the actual values, the difference between the predicted value and the actual value, the difference between these two, that is the residuals, right? The expectation is the residual should be symmetrical. What it means is basically the min and max shouldn't have a lot of variance. First quartile, third quartile should have less difference, and then median should be close to 0. So that's the expectation for your residuals. So we have this here. Now next let's jump into the coefficients. So as we saw here, it has a negative slope, so that's why you have your minus 1.017 as a slope for your LSTAT, and then you have your intercept, right? Your y-intercept is plus 33.97900, so that is your y-intercept, and then the slope for your h is going to be 0.03591. So remember, keep in mind this is a multiple regression or multi-dimensional regression. So that's when I try to plot my AB line, it was also showing since I was only using 2 dimensions and my model has more than one variable, so it was showing this, throwing this warning. I can always use add another variable in a separate plot, so it's all the same thing. Alright, so let's come back to the coefficients here. So you have your intercept, you have your slope of your LSTAT, your slope of your h. Now you can form your equation. So how does that equation look like? Your y is equal to mx plus c is gonna look something like this. So MEDV is equal to 33.97 plus 0.035 in times h minus 1.07 times LSTAT, right? So that is basically your linear regression line. That's what you have predicted, right? So these are the estimates. And then what you have on the next is basically your standard error. What does that mean? So this is the errors while it's trying to predict these estimates, right? So this is what you have here. Always, obviously it's an error, so obviously the less the best for you, right? So it's an error which is not something that you prefer. So always, what if it comes to less, it's amazing for you. And then you have your t-value. So what is your t-value? T-value is basically a division between your estimates on your standard error, right? So always the t-value should be the highest, because your numerator, when the numerator is highest, which means the estimate is highest and the standard error is lesser, which is it's a good prediction. And then you have your p-value. So p-value here, or the probability of probability value, like you see, this is the probability of your the modulus of t being the least, right? So what this means is basically you have 3 stars here, which is you have a mapping for these 3 stars. What does this 3 stars mean? For example, you have your when 3 stars means, which is a really good one, which shows that there is less error in predicting this specific estimate, right? So So what that means is basically 1,000th is the error rate for predicting your LSTAT's slope value, right? Likewise, this is just 1 star, which is basically here 0.01. So 1/10 is times of error, or 1/10 is the probability of error when predicting your slope of your age, right? And then again 1,000th is the probability of an error in predicting the estimate of your intercept. That is what the p-value means. Always, obviously, you wanted to have this as low as possible, so that your estimates are more closer to the accuracy, right? So that's why it's always amazing when it is gonna fall between 0 and 0.001. But usually, if it is like when you make a confidence level which is 1 minus your these values here, so it's whenever it is like 0.95 and above, it's amazing. Lesser than 0.95, you have to do some transformations within your data, like creating your logarithm of your x variables, like that. So like for example, in this one would be like log x, or log of age, or log of LSTAT, whichever needs to be treated, right? And now let's jump on to your residual standard error. What does this mean here? So this means that there is different values for residual standard error, like your root mean squared error, or regression error, or typical error, or people call it in different ways. It's all the same thing. This means is basically the error that you have, the difference between your y and y cap, which is basically your MEDV, and the predicted MEDV, the difference between these two. You just need to get the square of these differences, and then get the mean of that squares, and then take a square root of that. So that gives you your residual standard error, right? And then you have your degrees of freedom. So degrees of freedom is basically, there is a formula called n minus k minus 1. So that's how you compute your degrees of freedom. Basically, n is basically the number of data that you have. In this one, my training has 350 observations. So 350 minus, what is k? K is the number of coefficients that you have. So in this one I have two coefficients, LSTAT and age. So k is 2. So 350 minus 2, which is 348, minus 1. So that is 347. So those are the number of degrees of freedom. Next one, what you have is your r squared value. So multiple r squared value, what this means is basically, now the value that we have is 0.57. So this says that LSTAT and age, these two, in fact you can also add adjusted r square 0.56. So what it says is basically, since it's a multiple imputation, it's better to look into your adjusted r square. If this was going to be a single imputation using only one variable, I would have just looked into my multiple r square, but since it's a multiple imputation, adjusted r square, I'll tell you the difference between these two in a quite quick second. So in this one, I'm going to take a look into my adjusted r square. What it shows is basically LSTAT and age, they combinedly describe my MEDV at 0.56% accuracy, or there is 56% accuracy, or 56% of the variation in my MEDV is being explained by LSTAT and age, right? So that's what this value means. So what is, now let's come back to the difference between multiple r square and adjusted r square. Sorry, why I was using my adjusted r square for multiple imputation in place of my multiple r square, right? So why the reason for that is basically, so adjusted r square, this value is basically scaled for multiple parameters like these ones. So whenever you have a single parameter, it doesn't need to be scaled because there is only one parameter you are using as your input, right? So in those circumstances, multiple r square is fair enough, no problem. But then whenever there is more variables, you need to see their combined effect on the y variable or your MEDV, right? So that's why you need to scale these two variables to find the combined effect, and that's why you have your adjusted r square, which is always less than or equal to your multiple r square, right? So always it will be either equal to in some cases or less than your multiple r square. That's your adjusted r square. Finally, we have your F statistic or F test. So better to be lower, the lesser it is, the better it is for you. So F statistic explains how much of accuracy or how much of importance does the R square value has. The more the F static value is, the R square value tend to have more error, because R square value will always range between 0 and 1. So closer to the 1, the better it is for you, obviously, because there is when it is going to be closer to 1, let's say for example 0.90, there is 90% of variations has been explained by your input variables, right? So the F statistic value is always the lesser, the amazing it is, right? So for example, how you can do is basically how you can test that is you can add and drop different other variables from your data set. You have 14 different variables, right? So you can just add and drop different variables to your model. For example, you can add crim. There's a bunch of different variables. You can just put it in here and then try to find basically first your p-value, the lowest amazing it is, and then you have your R square value, and then also you can compare with your F statistic, right? So the lower these scores are, you will take that specific variable, and then you will go ahead and build your model. So that is your F statistic, and then you have your p-value again here. So that's what we have. So this is basically the meat of the full linear regression, right? So this is a really important piece in model building. Everything else is just basic programming. It's not a big deal, but understanding this is the important thing. Again, also what you have is, since we are doing the multiple regression, you have your residual plots, which I have explained in my other Alteryx video. You have your residuals versus fitted. So linear regression, there is 3 different principles of your linear regression, which needs to be set in stone. So what are these? So homoscedasticity, right? The output variable's value, it can increase, but then the residuals should not increase. It should not be proportional to the the value of your output variables, right? So that's homoscedasticity or funneling effect. So that's number 1. And number 2 is basically the residual should be normally distributed, and then you have your Cook's distance. There should not be a lot of effect of your outliers on your data set and these kinds of ones. So please take a look into my Alteryx linear regression using Alteryx video. I would have explained the residual plots in detail. So which is often necessary whenever you go ahead and build your multiple regression models, right? Alright, so now that we have built the model successfully, now let's go ahead and take a look into the predicted values, right? So I'm going to create a variable again called predicted values. I'm going to say predict, right? So that's a statistic based function that we have. I'm going to make use of that, call my model whatever I have built using the training data set, and then I'm going to pass my new data. That's going to be my testing data set, right? So as soon as I pass that, my predictions are ready for me to take a look, and then here you go. So these are the predictions I have. So now what I wanted to show you is to show the predictions in parallel with the actual predicted actual values. So what I'm going to do is test ds. I'm going to create a new column, predicted medv is equal to, that's going to be my predicted values, right? So now I'm going to take a look into my test ds. So you have your actual values. So these are your actual values and these are the predicted values. So you see this is there is some places it makes a clear, it's really close, for example the first one, and there are some places it's not as close. So this is basically the what you see, because your R squared value in this one, it is just like 50%, 55%, something like that. So that's why only 50% of the data has been the variations of data has been explained, and the remaining 50% is not well explained. You see these ones are all looking good, but there are some like these, you see some like these ones and these ones, 7.4 versus 2.8 and 18.2 versus 26. So these ones are all not well explained. So this is what this is your predicted value here anyways. So so what we discussed today is basically we took a look into the data set, we partition the data using random sampling, run if command, right? Straightforward. We partition the data into training and testing data sets, and then we created the model using training data set. And then once a model has been created, we took a detailed look into the summary of the data, right? What is your R square, what is your p-value, f-test, and all of that. And then we also took a look into the predicted values, right? So that's it from today, guys. So let me know if you have any questions. Thank you and have a good day.